Lewis structures provided one of the first simple models to show chemical bonding, and as such was limited in the way that it depicted the sharing of electrons. For example, in the compound you see here, sulfur dioxide, you see two valid Lewis structures, in which the sulfur atom is double bonded to one of the oxygens and single bonded to the other. Now, it's known that double bonds are shorter than single bonds. Yet, when sulfur dioxide is analyzed, you don't see the sulfur-oxygen bonds having different lengths. Both of the bonds between sulfur and oxygen are exactly the same length, somewhere in between a double bond and a single bond. In the actual molecule, some electrons are delocalized over several atoms, but Lewis structures cannot show that. The fix is to draw equivalent or resonance Lewis structures. So, when there are two or more valid Lewis structures for a molecule or ion that differ only in the position of the electrons, these are called resonance structures. Resonance structures of some compounds are not equivalent, as we saw they were in sulfur dioxide. For example, consider these structures. In the first compound, carbon is double bonded to both the nitrogen and the oxygen. In the second one, carbon is single bonded to nitrogen and triple bonded to oxygen. And in the third, triple bonded to nitrogen and single bonded to oxygen. All these are valid Lewis structures. Is there a way to tell which depicts the electron distribution in the most efficient way? There is a way, and it's called the formal charge. It's calculated for each atom in a Lewis structure as if all electrons were shared equally between bonding atoms. It's calculated as the difference between the number of valence electrons of the atom and the number of electrons that it owns in a Lewis structure. Now, we should take a minute to differentiate oxidation state, which we learned how to do back in Chapter 4. We used oxidation state to see if there was a change that would indicate that a species was losing electrons or gaining electrons. And the method in calculating oxidation state is to assume that all bonding electrons belong to the more electronegative element of the bond. In other words, even though it's a covalent bond, you pretend it's an ionic bond. It's not really, but you pretend that to calculate oxidation state so you can see if there's a change after the reaction occurs. Now that's different than formal charge. First of all, there's a different use for formal charge. It's used to determine which Lewis structure most efficiently distributes electrons. And the method for doing it is very different too. We assume that all bonding electrons between two atoms are evenly shared. In other words, we pretend that the bond is a pure covalent bond with no difference in electronegativity between the bonding atoms. So, if you were calculating for carbon dioxide the formal charge of each atom and the oxidation state of each atom, you'd see two different things. For the formal charge, each atom would have a formal charge of 0. We'll see how that's calculated in just a minute. For oxidation state, each oxygen is -2 for the oxidation state of the oxygen, and the carbon is +4. So how is formal charge calculated for each atom in a molecule or ion? It's simple. Formal charge equals the valence number of electrons of that atom minus the non-bonding electrons that are on that atom, the lone pairs, if you will, minus 1/2 of the bonding electrons. So let's calculate the formal charge for this oxygen on the left. You've got a valence number of oxygen it's 6, and there are 4 electrons, 2 lone pairs, or 4 electrons, belonging solely to oxygen. So that's -4. And then you have 4 electrons in this double bond to sulfur. You take 1/2 that number, and you get a formal charge on this oxygen of 0. The formal charge on the sulfur, again, the valence number for sulfur is 6. You subtract 1, 2, a pair of lone electrons, and you subtract 1/2 the number of bonding electrons, which is 1, 2, 3, 4, 5, 6 times 1/2. So you get 6 minus 2 minus 3, and that's a +1, so the formal charge on sulfur here is +1. The oxygen on the right has 2, 4, 6 lone pairs, minus the 6 valence number of oxygen, and then a bond with sulfur consisting of 2 electrons. Take 1/2 of that, so you have 6 minus 1, which is going to be a -1. Now the sum of all the formal charges have to add up to the charge of the species that you're working on. So this is a molecule with no charge, so the sum of the formal charges has to add up to 0. If you were working on an ion, the formal charge total equals the charge of the ion. Now I've got an easier way to do this. You draw a circle around each atom, and the circle bisects any bonds that the atom is making and wholly includes the lone pairs. So if we go to calculate the formal charge for this oxygen, we have 1, 2, 3, 4, 5, 6. We only count half of these bonding electrons to sulfur. The half which is depicted within the circle. And you know, a fast way to do that is to just start with 6 and then subtract 1 as you go along. So we have 6, 5, 4, 3, 2, 1, 0. Formal charge in this oxygen is 0. Okay, let's do this sulfur. Valence number 6, 5, 4, 3, 2, 1. Formal charge is +1. How about this oxygen? Start with 6. And then 5, 4, 3, 2, 1, 0, -1. So that's a much quicker way to calculate your formal charge. So let's figure out the formal charge for each atom of carbonate. Okay, and we'll use our simplified method here. First, a circle around this oxygen, bisecting this double bond in half. We start with 6, which is the valence number of oxygen. 5, 4, 3, 2, 1, 0. So the formal charge for this oxygen is 0. Now, let's see, we bisect this bond and go around like this. 6, 5, 4, 3, 2, 1, 0, -1. So this oxygen is -1. And do the same for this one. And let's see, that's 6, 5, 4, 3, 2, 1, 0, -1. So that's a -1. Now, according to my calculations, -1 and -1 is -2, and this thing has a charge of -2. So it seems to me that the carbon needs to be 0. Let's find out if that's true. Put a circle around the 0. And carbon is 4, and so that we start at 4, 3, 2, 1, 0. And yes, carbon is 0. So there it is. Each of the single bonded oxygens is -1. Carbon is 0. And the formal charges add up to -2. All right. Now let's calculate formal charge in resonance structures that are not equivalent. We mentioned this before, where you had carbon, in one case double bonded to both nitrogen and oxygen, or single bonded to nitrogen and triple bonded to oxygen, or vice versa. Which is the best and most stable Lewis structure? What we need to do is figure out the formal charge for each atom in each of the three structures. And then the best structure will have, first of all, the formal charges closest to zero, at least extreme, or that we have, or that we have negative formal charges on the most electronegative atom. Okay, so here we go. Let's figure out formal charges for this. We'll put our circle around nitrogen. Nitrogen has a valence of 5. So 5, 4, 3, 2, 1, 0, minus 1. So this nitrogen is minus 1. Carbon is, I can see, going to be 0 here. This carbon is 4, 3, 2, 1, 0. So this carbon is 0. And this double bonded oxygen is probably going to be 0 too. Why? Because this ion has a charge of minus 1. I've already got my minus 1. So the formal charges have to add up to the charge of the ion, and it does already. So this oxygen should be 0. Let's see. Oxygen is 6, 5, 4, 3, 2, 1, 0. Yep. So this one has a minus 1 on the nitrogen. Now let's try this structure. All right. We'll figure out the formal charge for this nitrogen. It's 5, 4, 3, 2, 1, 0, minus 1, minus 2. Carbon is going to be 0 probably, right? 4, 3, 2, 1, 0. So the carbon is 0. And the oxygen is going to be 6, 5, 4, 3, 2, 1. So this oxygen is plus 1. And yes, minus 2 and plus 1 add up to minus 1, and that's the charge of the ion. So that's a check that our formal charges are right. Okay, the last compound is going to be this one. Let's do this. Around the nitrogen, 5, 4, 3, 2, 1, 0. So this nitrogen is 0. Carbon is going to be 4, 3, 2, 1, 0. Carbon 0. This oxygen is going to be minus 1. 6, 5, 4, 3, 2, 1, 0, minus 1. So there's our minus 1. So it's not going to be this one because this has the most extreme range of formal charges, minus 2 and plus 1. And so we can leave that out. This one has a minus 1 on the nitrogen, and C has a minus 1 on the oxygen. And rule 2 is the negative formal charges are on the most electronegative atom. So we have a minus 1 on the electronegative oxygen here. So it looks like this structure here is the most efficient distribution of electrons and contributes most to the resonance hybrid. Okay? Now, we have another set of rules here. Again, this is not in your textbook, and it's called the rules of normal covalency. And the rules are, hydrogen only gets one bond going to it, a single bond. Oxygen gets 2 bonds going to it, either 2 singles or a double bond. Nitrogen will have 3 bonds going to it, single and a double, or a triple, or 3 singles. And carbon gets 4 bonds, either as 4 singles, or a double and 2 singles, or a triple and a single, or 2 doubles. So if you're writing a structure which doesn't have a charge, it's not an ion, it's a molecule, you can very quickly put together the structure of the molecule without resorting to Lewis structures, just by following these rules. So let's do this. Let's use these rules to draw out structures for these two compounds here, the rules of normal covalency. First of all, C2H6O, what I'm going to do, carbon and carbon, okay? Now I've got 6 hydrogens, so I'll put the hydrogens on each carbon, like that. Okay, that's 5 of them. If I put another hydrogen here, I won't have any place to put the oxygen. So I can put my oxygen next on this carbon and then top it off with a hydrogen. Okay, there's another way you can put this molecule together. Can you do it? All right. And I want you to practice doing this one. And we will do this in class. See if you can write out a structure for this that obeys the rules of normal covalency. And then can you draw out this compound, C4H8, that obeys the rules of normal covalency? In fact, why don't you turn off the playback and come back to this, and then I'll show you how to do it, okay? You try it. Okay, let's see if we can put this together, all right? So we have 4 carbons. Let's put that in a chain like that. And I have 8 hydrogens. So I'll start to put on my hydrogens. Hydrogens only have 1 bond going to them. So I'll put 3 on this carbon. Now this carbon has 4 bonds going to it. And this hydrogen and another. Let's see, that's 5, 6, 7. 1, 2, 3, 4, 5, 6, 7, 8. Okay, I've got this structure now with 4 carbons and 8 hydrogens. And I don't have enough hydrogens to saturate this. In other words, this carbon and this carbon only have 3 bonds going to it, not 4. So this is an example where we would need to use a double bond between the 2 carbons to obey the octet rule for these 2 carbons. Now we have 8 electrons around this carbon and 8 electrons around this carbon, and we have our hydrogens all in place. So this is a good fit. Now we're going to talk about some patterns in bond length and bond strength. The shorter a chemical bond, the stronger that bond is, and the more energy it takes to break that bond. And smaller atoms make shorter and therefore stronger bonds. So what I want you to do is rank in order of increasing bond length and decreasing bond strength: carbon-fluorine bond, carbon-chlorine bond, and carbon-bromine bond. All right, let's see if you can do this. The carbon-fluorine bond has a length of 135 picometers. That's 135 times 10 to the minus 12 meters. Its energy is 488 kilojoules per mole. The carbon-chlorine bond is longer, 177, and its energy is smaller, 330 kilojoules per mole. Carbon-bromine bond, because bromine is a larger atom still, is 194, and the bond energy of carbon-bromine is even less, 288. So as the bond length gets longer, the bond strength gets weaker. So here are some bond lengths. Carbon-to-carbon bond is 154 picometers. Silicon to silicon bond is 234. Sulfur to sulfur is 204. Which is the strongest and which is the weakest of these bonds? Well, here it is. Carbon-to-carbon bond is 154. Its energy is 83 kilojoules per mole. Sulfur to sulfur is 204 picometers. That's only 54 kilojoules per mole. And a silicon to silicon bond is 234 picometers, and its energy is 52 kilojoules per mole. What about multiple bonds within carbon? Bond length of carbon-to-carbon single bond is 154. Carbon-to-carbon double bond is 134. Carbon-to-carbon triple bond is 121. Can you rank those in order of bond strength? So here we go. The carbon-to-carbon single bond, 154, its energy is 348 kilojoules per mole. Carbon-to-carbon double bond is shorter, therefore stronger. The energy is 614 kilojoules per mole to break that bond. And carbon-to-carbon triple bond is 121 picometers. Its energy is 839 kilojoules per mole. Now we're going to talk about trends in acidity and basicity. This isn't in your textbook, so pay attention because you will be asked this. Oxygen bonded to metals produces primarily an ionic bond because there's such a large difference in electronegativity between oxygen with an electronegativity of 3.5 and a metal like sodium, which is 0.9. So the larger the difference in electronegativity, the more ionic the bond. And when this substance is hydrated, you get a split between the positive cation, the sodium ion, the magnesium ion, and the hydroxide that forms after the oxygen is hydrated, forming a hydroxide, OH-, which makes the solution a basic solution. So this happens to metals combined with oxygen, either at the far left side of the periodic table or at the bottom of a family of nonmetals toward the bottom. Antimony, bismuth are acting more like metals, big difference in electronegativity, and you get the hydroxide formation. For example, if you put sodium oxide in water, it hydrates to form 2 moles of sodium hydroxide. And of course that's going to split between the sodium and the hydroxide to form an ion of sodium and an ion of hydroxide. And that is going to be a very basic solution. The hydroxide ion makes the solution basic. Now what happens instead if oxygen combines with a nonmetal like nitrogen or sulfur or phosphorus or even a halogen, chlorine? What happens in those situations? What you have are primarily covalent bonds, albeit polar covalent bonds between oxygen and the nonmetal. And that makes it tough to break that bond. It's a covalent bond. So let's, as an example, take some dichlorine heptoxide here and put it in water. What we get is 2 moles of perchloric acid, one of the strongest acids we know about. Now this is confusing. If you just look at HClO4, you don't really see why it's an acid. It's better to look at the structural connection of where the hydrogen really is bonded, so you can begin to understand that you have an OH bond, not an HCl bond here, but an OH bond. But the oxygen is covalently bound to the chlorine. And all these other very electronegative oxygens are also on the chlorine. And that strong difference in electronegativity pulls the electron density away from the OH bond, making it very easy for H plus to migrate from this molecule to, say, a water molecule to make hydronium ion. In other words, this is an acid. It's a proton donor. It generates H plus, which is taken on by a base, which has a lone pair of electrons. So this occurs either at the far right side of the periodic table or at the top of a group or family of nonmetals like nitrogen and phosphorus. You've all heard of acid rain, and this is exactly why we have a real problem in burning fossil fuels, especially coal, where there's a lot of sulfur in the coal, and the sulfur combines with oxygen to make sulfur dioxide and sulfur trioxide, mixes with rainwater to form sulfuric acid H2SO4, again very acidic, a great proton donor. So could you please arrange these element oxides in order of increasing acidity now that you've heard my little spiel on this? And here's the table to help guide you in doing this problem. We'll ask you this in class. It's possible to get a good estimate of the enthalpy for a reaction by looking at the enthalpies of all of the bonds of the reagents and of the products. When you sum the enthalpies of all the bonds of the reagents, you're breaking those bonds, and therefore the total enthalpy would be endothermic or positive in value. And if you take the total of all the bonds being made on the product side, when bonds are made, energy is released, and that total is going to be negative because it'll be an exothermic process. So you add the two up and you will get an estimate for the enthalpy for the whole reaction. So let's do this. Methane plus chlorine yields dichloromethane plus HCl. Let's try it out. On the product side, we'll do that first. We have two CH bonds here and here. And each one of those is 413 kilojoules per mole. And those bonds are forming, so that's minus 826 kilojoules. The carbon-chlorine bond, we have two of those in the product. That's 339 each, so that's minus 678. And we have 3 moles of an HCl bond being formed, 427 kilojoules per mole, so that's minus 1281. So the total is minus 2785 kilojoules on the product side. Now let's do the same for the reagent side. We have 4 CH bonds. 4 times 413 is 1652. That's positive because we're breaking those bonds. Chlorine to chlorine is 243. We have 3 of those. That's 729. We add those up. That's a positive 2381 kilojoules. So to get the total, we add them. Now, don't make the mistake of doing it the old way with products minus reactants. Don't do that. In this technique, you take the sum of one and the sum of the other and you add them together, just keeping in mind that on the product side, that the total is going to be negative. On the reagent side, the total is going to be positive, and you add them together. In this case, you get minus 404 kilojoules. This is an exothermic reaction with 404 kilojoules produced. Okay, let's see if you can do one now. The combustion of methane is methane plus 2 moles of oxygen yield carbon dioxide and water. The oxygen is double bonded to itself, and the carbon dioxide, the carbon is double bonded to each oxygen. So here are all the bond energies for that, And can you use these bond energies to estimate the enthalpy for this reaction? Turn off the playback, see if you can do it, and come back and you can compare your answer to mine. Okay, here we go. We have two carbon to oxygen double bonds in the carbon dioxide. That's minus 1598 because those bonds are forming. And we have 4 moles of hydrogen to oxygen bonds. That's 4 times 467, or minus 1868, for the total of minus 3466, the exothermic process of putting all these bonds on the product side together. On the reagent side, we've got the methane. That's 4 hydrogen to carbon bonds, 4 times 413. That's a plus 1652. And we have 2 moles of oxygen. Oxygen's double bonded, so that's 2 times 495, which is plus 990. Total plus 2642 kilojoules. So you add these two together. Did you get minus 824 kilojoules? If you did, you're right on. Very good. So finally in this chapter we're going to talk about metallic bonds.
Metal atoms have few electrons in their valence shell, and these are relatively weakly held. Though metal atoms group together in a crystalline lattice structure, they have very different properties to the ionic solids. For example, solid metals are able to conduct electricity. This is because the loosely held valence electrons of metal atoms are delocalized. They are not bound to one atom. Instead, they can move through the lattice in all directions. A sea of delocalized valence electrons surrounds the crystal lattice of the cations. The structure is held together by the strong electrostatic force between the sea of valence electrons and the metal cations. This is called metallic bonding. The electrons are constantly on the move, so the bonding acts in all directions. Metallic bonding is powerful enough to overcome the force of repulsion between the closely packed cations. The high melting points of most metals indicates the strength of the metallic bond.
This model shows very strong attractions of the nuclide to delocalized valence electrons because there is no shielding of these valence electrons. Therefore, small light electrons can move easily throughout the metallic solid, and they can transfer kinetic energy more quickly than larger particles that are locked in position. So metals are excellent conductors of heat. And because the attractive forces holding the metal crystal together are very strong, metals usually have very high boiling and melting points. The blacksmith pounds this iron to shape it to her will. Metals are malleable, able to be pounded without shattering, even into very thin sheets. Because when metal nuclei are pushed around, the repulsive forces between them are neutralized by the flow of electrons that surround them. Ionic crystals, on the other hand, break when hit because the like charges of shifted ions repel each other. Of course, metals conduct electricity well because electrons are able to move through the structure, flowing from negatively charged areas with an excess of electrons to positively charged areas with a deficiency of electrons.